Good morning everyone, and welcome to today's worked exam answer video. Today I'm going to be having a look at a KC question at the request of one of you lovely followers, and there will be a KP question to follow later this week so that we can have a think about the ICE tables, as I'm sure a lot of you will know them as. So initial moles, changing moles, equilibrium moles, and then this one's also got a calculation involving a rearrangement of KC, and then we've got a bit of an equilibrium question at the bottom, thinking about the Chatelier and which way the position of equilibrium is going to move, and thinking about the terminology that we need to explain that. So printed this from a PDF, so I'm going to do my working out on the lined paper instead today, but otherwise everything will be the same. So we've got our equation for our equilibrium mixture. We've got A and B reacting together to form an equilibrium mixture containing C and D. Now in part A, we're going to need to use an ICE table. A couple of things that they've done differently here that they definitely don't always do is, instead of giving us the moles of A that they've added to the beaker, they've instead given us a volume and a concentration, which is fine because we can turn a volume and a concentration into moles nice and easily, but that's one of the reasons why we're getting more marks for this kind of question. And then the other thing that's a bit unusual is, as well as then having B, our other reactant in the beaker, and again they tell us how much of that they add to the beaker at the start, we're also adding one of the products into the beaker in the first place, which we can do. We're going to deal with the ICE table in the same way, but rather than saying, oh well, we've got 0 moles of C and 0 moles of D in the beginning, we don't have 0 moles of C, we have 2.8 times 10 to the minus 2. D doesn't mention, so D, there will be none of D in the beaker at the beginning. That's then left to reach equilibrium. So this is our information for our initial moles of A, B and C. Then we're given the moles of A at equilibrium. So using the initial moles of A and the equilibrium moles of A, we can figure out how much of A is reacted. Then using the ratios from this equation, we can see how much of B needed to react with A, and then how much of C and D have been made. And then for C, we can add what we had initially to what has been made. And that's exactly what we're going to do, calculate the amounts in moles of B, C and D in the equilibrium mixture. So, starting with my ICE table, so I like to have the equation as like my column headers, and I'll keep the ratio in there as well so that it's there for me. And then on the side I want to have initial moles. I'm just going to call it initial. And then if you know it as an ICE table, you'll do change in moles next. I usually do reacting moles, but it's the same thing. So I'll go with change because that I think is what most of you will be familiar with. So the change in moles is how much we either lose if you're a reactant or how much we gain if you're a product. So I would always have a negative number for the reactants for my change row, and then a plus for my products in my change row. And then we're going to need equilibrium moles. And you might be thinking, well, why on earth do we do this? Because it is from the equilibrium moles that we then get the equilibrium concentration, so that we can work out a value for Kc, which shows us essentially where the position of equilibrium is lying, more to the left, more to the right, fairly central. So first thing we're going to need to do is sub the numbers in that we have. So initial moles of B is 9.5 times 10 to the minus 3. Initial moles of C, 2.8 times 10 to the minus 2. There was nothing for D. And then the initial moles of A, we need to use the volume and the concentration. So volume will obviously need to be in decimeters cubed, so 0.04 decimeters cubed times by 1.6, because moles is concentration times volume. That gets me 6.4 times 10 to the minus 3. and I will put underneath for you that it's 0.04 decimeters cubed times by the concentration. That's how I got that. Okay, so that's got to be the first thing we do with these ice tables, and then for whichever substance we now know the equilibrium moles of, that's the next thing to write in. So the equilibrium mixture formed contained 3.9 times 10 to the minus 3 moles of A. And from that, we can work out everything else. So first thing, whichever substance you now have both the initial and the equilibrium for, we can figure out the change by doing the difference between 6.4 times 10 to the minus 3 and 3.9 times 10 to the minus 3, which gets me 2.5 times 10 to the minus 3. And I've written that as a minus, like I say, because that means we're losing some of reactant A as this approaches equilibrium. Now this is where we need our ratio. So our ratio is 2 to 1 to 3 to 1. Have I copied that down right? Yes, I have. So in order to work out the moles of B that we've lost, it's going to be half of the amount of A that was lost. So minus 1.25 times 10 to the minus 3. And then I can figure out how many moles of B would be left at equilibrium by doing the 9.5 take away the 1.25 times 10 to the minus 3. And that gives me 8.25 times 10 to the minus 3 moles of B left at equilibrium. Now, based on my significant figures, I should really write that to 2 significant figures, because everything else that we've been given has been to 2 significant figures. So I'll just update that. And now we can also fill that in for D, because B and D are in a 1-to-1 ratio. So we're going to make, so plus 1.25 times 10 to the minus 3 moles of D, which, because we didn't start with any, is going to be 1.25 times 10 to the minus 3, which again I will rewrite as 2 significant figures to match everything else. And then for C, we are going to make 3 times as much as we made for D. So I'm going to need to multiply the 3.125 by 3, which is going to get me 3.75 times 10 to the minus 3. And then that is going to be added to the original 2.8 times 10 to the minus 2 that we had, which gets me, sorry, it's not giving me my answer in standard form and I want to keep everything the same, 0.03175. So 3.2 times 10 to the minus 2. That took a little bit too long for my brain, my apologies. And then they are our moles in the equilibrium mixture. So we figured it out for B, C and D as the question wanted and got 5 marks for doing so. So key things, copy down the information that you know for the initial moles and whichever you know for the equilibrium. Whichever one you have both initial and equilibrium for, work out change. Using the ratios, work out the change for everything else, and then do for reactants, initial take away the change, and for products, initial add the change. Okay? Now next up we have to give the expression for the equilibrium constant Kc for this equilibrium and its units. So the little c after the K stands for concentration. So in a Kc expression, we should always use square brackets. And for any equilibrium constant, it's always products divided by reactants. So we're going to have the concentration of products on the top divided by the concentration of the reactants on the bottom. The balancing numbers in our balanced chemical equation give us the powers where relevant. So we're going to have the concentration of C will be cubed, times that by the concentration of D, and these are times together, not add, by the way. And then on our reactant side, we're going to have the A, and because of the 2, we're going to square, and then times that by the concentration of B. Now the units of Kc will vary. and that's why they're asking us to give the units here. All of these concentrations are mole per decimeter cubed, like every normal concentration is. We've got a total of 4 lots of concentration units on the top, and you can write that out 4 times: molybdenum minus 3, molybdenum minus 3, molybdenum minus 3, molybdenum minus 3. We've got 3 on the bottom, so again you could write molybdenum minus 3 times on the bottom. If I have 4 on the top and 3 on the bottom, 3 from the top will cancel with all of them from the bottom, leaving me with 1 lot of units on the top. So 1 lot of mole dm minus 3. Had that have appeared on the bottom, say our equilibrium was the other way, upside down, we would have 1 over mole dm minus 3, and if you have 1 divided by the leftover units, you flip the sign, so it would become minus 1 and plus 3. Any queries on that, of course, just let me know. Now, this is fairly common for KC questions. You'll do all that hard work with your ICE table, and then they'll come to doing the calculation and they'll give you some new numbers. And I get why, because if you weren't able to do part A, that would then completely scupper you for the next part of the question, and AQA are very fair and don't want you to be penalised for something you can't do more than once. So they've given us some new equilibrium information for the same equilibrium but at a different temperature. We've got 0.21 moles of B, 1.05 moles of C, and 0.076 moles of D in a total volume of 5 times 10 to the 2 centimetres cubed of solution, and we're given a value for Kc. So we're not working out Kc, we're having to rearrange the Kc expression to calculate the concentration of A, and we have to give our answer to the appropriate number of significant figures, which, looking at what we've got in the question, is going to be 3. So let me just make a little note of that. Okay, so volume, I have no idea why they've chosen to write it as 5 times 10 to the 2 centimetres cubed. First of all, that would be 500 centimetres cubed. And then if we're changing these moles into concentrations, we need the volume to be in decimetres cubed. So that might be something that you wish to do first off. Now what you can do is calculate each concentration, so it's not uncommon to see equilibrium moles and then, if relevant for the same question, a row for equilibrium concentrations. I am going to put everything as 1 into my expression and kind of do it that way, but you can work them out individually and then sub the concentrations in. It's whatever you feel most comfortable doing. So the first thing that I'm going to do is rearrange my Kc expression. So if we want to figure out the concentration of A, I need that to be on its own over here. So I'm going to times up by the A squared and then divide and put Kc in its place. And then once we've worked out the concentration of A squared, we can then figure out the concentration of A by square rooting whatever answer we have at that point. So then I'll put Kc on the bottom in its place and times that by the concentration of B, and I'll figure out what that is first, and then I'll square root that. So the moles of C, 1.05, so therefore for C it's going to be 1.05 for the moles divided by our volume of 0.5, and then that needs to be cubed, and then we're going to times that by D, which is 0.076 moles, again divided by the volume, 0.5, and we don't need to cube, square, do anything with that. Then we've got the value for Kc, which is 116, so 116, and then for B, number of moles wise, 0.21, and again same volume, 0.5, and again I don't need to square or cube that. Now if you feel comfortable, you can put all of that in your calculator in one go. I have done it and it's just making sure that you've got a suitable amount of brackets and in the right sort of places. So I've got my moles over concentration in brackets cubed times the next moles over volume, and then all the top of the fraction in brackets, and then on the bottom Kc times by, and then moles over volume for that concentration in brackets. You can see that gets me an answer of 0.02889. So that is then our value for the concentration of A squared. So therefore, the concentration of A, which is what the question was wanting, to the appropriate number of significant figures, which we said was 3, I'm going to need to square root my answer of 0.0289, which gives me, annoyingly, 0.1699797148. Annoying because to 3 significant figures it's going to have to be 0.170. And the 0 at the end is very important. It's a concentration, so let's also give it some units. There we go. Now with these questions, the way you show you're working out is imperative, because let's say we type something in wrong and we got the wrong answer for A, they will want to go back and give you working out marks. So usually it's 1 for rearranging the Kc expression, 1 for subbing the numbers in, and then 1 for your answer. That would be for this case with the 3 marks, so it's really important that you do show those steps. Okay. And then finally, justify the statement that adding more water will lower the amount of A in the mixture. So the amount of A is decreasing. And if the amount of A is decreasing, if we're thinking about Le Chatelier, what has to have happened for A to go down is the position of equilibrium has to have shifted to the right. That will cause there to be less A in the mixture. So why would adding water cause that to happen? Well, adding water is going to dilute everything because they're all in the same beaker. So if we add water, we're adding water to everything. So all of the concentrations will be diluted in the same way. And this then becomes essentially like a pressure question. So if I've then diluted everything in order to increase the concentration back to what it was before, it's going to favour the side with the most moles of particles, because that would then, in the new bigger volume, would give us a more concentrated solution, because there'd be more moles in whatever the new total volume was. And that's why position of equilibrium shifts to the right, and that's why we lose some of our A. So when we're thinking about our Le Chatelier answers, we do need to think carefully about the wording that we're going to use. So I would always say which way the position of equilibrium is shifting, what is being favoured, and why is it shifting in that direction. So to oppose, and then whatever the changes that we've put on the system. So here it'd be doing it to oppose the dilution of the solution, or to oppose the decrease in concentration of the reactants and products. Okay, so the position of equilibrium will shift to the right, and then my second bullet point would, well, I can write it all in one sentence, but the second part would be saying to favour the side with more moles to oppose the dilution of the reactant and product concentrations. And in some questions it might ask you to say what would happen to the yield of a reactant and product. Sorry, I'm trying to write and speak at the same time, I should know better. And if they do, ask you to say what's going on in terms of what happens to the yield of something, then of course that would be something to build into your answer as well. So let's just say this said we add more water, what would happen to the amount of A? You would then get a mark for saying that the amount of A would decrease. And then you can add that to the start of this sentence, so the amount of A will decrease because the position of equilibrium will shift to the right to favour the side with more moles to oppose the dilution of the reactant and product concentrations. Ta-da! Hopefully that was useful, particularly for the person who requested such a video. There will be a KP one, like I say, in a couple of days, and any other requests that people have, please do not hesitate to let me know. Any questions about this video, as always, please leave me a comment and I will get back to you as soon as I can. Thanks so much for watching, guys.